Okay, so today I'm going to talk to you about what is called inorganic chemistry and metal complexes, and this one is give you an overview. In the discussion section, as I showed it before, the nomenclature is very important for understanding the metal complexes. Okay, and then I would like to blow up this section that this is what you learn from what you see in your lecture slide, and they are very commonly used what they call the ligand. Ligand is one that give out the lone pairs, making a coordination complexes, and even EDTA. EDTA is a long mouthful one. Honestly, I don't remember the name of the EDTA unless I can look up. I can always look up. But EDTA is so common that is a very, very strong the ligand that can bind it to the metal complexes. And oxalate ion is coming from the oxalic acid. Ethylene diamine is there are two amines, and then this one is a tetraacetate. Okay, so I'm highlighting those. These are the one that reaches on lone pairs. Right. So these are the one lone pairs, and the metal is usually in the center of the metal complexes. They are the one usually positive charges. So these are the ligand, and then this one, the effective number of the ligand is, I would say, this is a 2 dentate. This is a 4 dentate. So when the EDTA bind it to the metal complexes, they really stick to it. It's almost like you have two hands and you have four hands grabbing onto the metals and for the EDTA, whereas the ene, which is an ethylene diamine. So this is ethylene, right? This is an ethylene diamine, so two amines, and this is one looks like there are two grabbing hands. So sometimes the people just draw this way, right? And so and then those two, the lone pairs I'm just highlighting is the one that connect is clinging to it. So give a name that because this OX, oxalate ion, and the diamine and the EDTA ions are quite forming a multi-dentate, multi-coordination complexes, and these are the quite ligand. There are other ligands, and so this is the common ligands, and because the metal complexes, they are either anion, well, they are neutral molecule, but neutral molecule should have a lone pair electrons. And so we call the bromine chloride and bromide chloride, and then they have a negative ion, and hydroxide ion, cyanide ion, and the nitrite ion, and oxalate ion. And this one, so whenever this is an anion, you see the common name, it ends with an O, right? So even the oxalate is with an negative 2, so oxalato is one that they using their name notations. So make sure that O it ends with an O means an anion, which is a negatively charged species. And I don't know what this author has make a name. If you look at an EDTA, you see this? EDTA is a -4, right? And -4. So, and then actually they made it the right way. It's an anion. It should be going underneath. So tetra 4 acetate, right? Acetate. So it becomes let me clean it up here. Acetato, right? So you end it with this O at the end to make sure that they want to represent this one is an anion there. And then those who are not anions and the neutral, they have their own name. Water is an aqua, and ammonia is aminin, and the carbon monoxide, which is a carbonyl, and then ethylene diamine we call EN. That's an ethylene diamine because these are the neutral molecule, and as you can see that it has a lone pairs on oxygen, nitrogen. This one is actually the carbon has a carbon and the oxygen both have a lone pairs, electrons, and then this one is essentially, okay, so again it's a diamine with these lone pairs, and I think the EN shows quite a lot of time in the past problem set I've dealt with so far. So there's one other thing that I wanted to show, which is what is called let's have a look at it, the cyanide, okay, the CN. CN is actually having this triple bond with two lone pairs like this, and because if you count the number of hole, the valence shell electron, there are 10, and so this is how they do. And so if you look at the former charges, carbon is right there, and this is the overall negative charge. So this is more negative, so this is more likely the one that is what is called the lone pair electron that docking, making a connection to the central atom, because that's the compound. But we'll discuss it about this one later. The cousins of cyanide ion is what is called SCN minus, and the structure is SC triple bond minus with those connectivity. Okay, so this one overall is a minus charges, and the minus charges concentrate on here, and so therefore these lone pairs on the sulfur is the one that connected to the likely to connect to the center of the metals. Okay, and the name for this one is essentially thiol. Thiol means a sulfur, and then cyanoto. Okay, so it's a negative ion, thiol, sulfur containing cousins of cyan, CN. Right. So this is this is a negative charge. So this name is essentially can be find out from this component. The thiocyanato is the one that you can find it from there. And also I'm going to show you the so if I solve the problem on the diethylene diamine, and so this is let's have a look at it. Okay, so this is a bromine. Bromine is a negative charge, so overall complex is plus charges, and then but the chlorine here give out -2 charges. There is no charges to make the overall. The cobalt here must be 3 plus. Okay, so therefore what I can see here is, okay, so cobalt is 3 plus. Cobalt is 3 plus. Okay, so that's the first one that I know. And the second one that I need to start to figure out is, okay, what are my options? Okay, this is EN means ethylene diamine. And there are two of them, so it's a diethylene diamine. And then there are 2 dichloro. Okay, so those are the components that should go into the name. And the last one is this is what is called a bromide. Okay, that's at the end. So which one comes first? You should put the ligand before putting the metal complexes. This is an E. This is a C. And it goes by alphabetical order. So I will put dichloro, diethylene, diamine, cobalt 3, and bromide. It's a long name, but if you're looking at the components, I think that you guys can handle that. Okay, dichloro, 2 chlorine, dien, right, diethylene diamine, and cobalt has a +3 charges, and the bromide is a bromine with a minus charges. and they form these complexes. And so the purpose of this is, by writing this, you should be able to write this chemical structure right there. And then I actually pick up the problem where you can see the cis and trans geometric isomers on this case, where this cobalt complex with the 2-diene, they can form these octahedral structures. So I think that this is a similar problem that was a chromium complexes in your discussion problem set. This is a red plane I'm trying to visualize to you that the plane that is more likely on the flat plane, and then your cobalt is sitting inside of it. Okay, so the cobalt is sitting at the center. I think that we already know cobalt was 3+ from the nomenclature that I picked an example. That's a 3+. Okay, so I got that. And octahedral means there is something that sticking up, and then there's something that's sticking down. And then there are 4 other things that are forming the coordination. So there are 1, 2, 3, 4, 5, 6. So these are actually 6 positions that we call the octahedral. They are forming the equivalent positions. And what you can see here is from this cobalt En2 and Cl2, we can focus on this one is more like Cl. You can think this one is okay. This is A4 B2. Okay, you can generalize these categories because this is a more likely have a didentate, so they have 2 coordinations. So having 2 of 2, so effective number of coordination is 4. So this is from that the En numbers. So I can focus on essentially the chlorine here. Okay, and the chlorine can be shown up here and here, forming this 90-degree, or they can go up and up. And that's a second example. Okay, so let me this is a chlorine up, chlorine down. So once you put this one up, you have to connect these 2 dots. This is I'm trying to show you this ethylene diamine. So one is in the axial axis and the other one is in the plane. So these are the 2 enes, and whereas this one is both amine nitrogens forming the complexes like this, and their lone pairs are essentially facing towards the cobalt. Oh, okay, so I have to go up. Cobalt showing up in the middle. Okay, so that they are essentially give out these lone pairs, trying to making an effort to neutralize central metal complex ion. And when you have a case just looks like this, and particularly you have this compound with a En with a dichloro, and this figures, this one shows, okay, this is a cis and this is a trans. And trans is much easier to understand because this means an opposite side, and cis means they're on the same side. Okay, same side. And you can see that it's pretty clear that chlorine is the opposite side, whereas this one, when you put the chlorine here and the chlorine in the other side, they are opposite side. Okay, but when you put the chlorine here and the chlorine onto this side, this is a neighboring side. So it's not same side. It's actually better word is neighboring side. Neighboring side. is a better one. So it's not 180, but it's a 90-degree side. When you put this one, whichever you do is all 90 degrees, right? So think about, I can put another example here. If I can put the chlorine on the top, and any position on there, if you put the chlorine, and these are all 90 degrees. Whereas except for the one in the opposite side, just like here, there's a trans. Okay, so, and if you have this is if you look blow up this version, this is the cis. The metal complexes cobalt with En2Cl2. Okay, and so they are the one who having this chlorine on the 90-degree side. And then if you put the mirrors, and this is a flipped mirror images, and then once you have this flipped mirror images, and you can bring this one down, and if you rotate this one like this, and you will find yourself, and this one and this one, these positions, the ions are different. They are not same. Okay, so this is what is called a non-superimposable, means. This is a cis complex, and this cis complex, they are chiral isomer pairs. Okay, so they are so therefore this cis isomer, they can have chiral isomers. Okay, so they can have chiral. Can have chiral isomers. Whereas this one, if you look at the chlorine, if you put down the mirrors, and the flip side of the mirror would not going to have a different one. So what that means is, if you do the same thing with the trans showing up here, if you put down the chlorine on the axial position, if you do put the mirrors and trying to look at the mirror image molecule, is whether they are superimposable or not. And trans cases, they are superimposable. So there's the same molecule essentially, whether the mirror reflection or not. So therefore, trans is cannot have chiral. Okay. And this is another picture that this is if you look at this compound, this is your class slide that I find out, and this is cobalt with essentially diethylene diamine. There are 3 of them. Okay, so those are the complexes. If I say probably this will be a 3 plus, and so this is forming the complexes, and for that, and this one is essentially form the plane with the cobalt in the center, and then there is an axial position, and then there are 4 positions on the equatorial or on the plane. Okay, so these are position, and depending on how you connect those, okay, these 3 connections for these amines shown as a big black dots, they can have a chiral isomers. So this one is showing that if you put this one to put a mirror images, now you can see that, and bring this one and rotate yourself, and you'll find out this connected to this and that connected to that, whereas this is and that is not the same, right? This part is superimposable, but these two from the axial to the back and from the lower axial to the right is not superimposable. So therefore, this one is always they can have a chiral. Okay, so I think that you might have refresh your memory before. Do you remember the tetrahedral carbon, and to have a chiral isomers, you need to have 4 different attachments: alpha, beta, gamma, delta. So and then this is always a chiral center, and I think the Chem 1 class we use this carbon with has to be sp3 carbon, and we are putting a star sign. That's for what is called the chiral center. That's what we cover in the Chem 1. But what we are saying here is this is an essentially octahedral structure, but this is essentially chiral center. And I think the probably lecture note didn't use the notation, but I can put a star sign just like that because of this octahedral structure also can have a chirality. Actually, depending on the ligand, how the ligand is arranged. And here I show you that this is a chiral, and in fact, actually, for the exam part, this is one of the exam problem that which one is chiral. This is an example of the chiral, and also this one. This is chiral, okay? And I think that you want to remember that as well. Okay, so I am going to continue to solve this cis and trans. So this is a cis and trans isomers, and this is a same slide that is shown up here. And then there's something called FAC and mer isomerism. And this is something about 3 identical ligand. So this is more like about a little bit expansion about different types of isomers. And we call the geometric isomers. There are 2 types. And geometric isomers is let me use a consistent color. So geometric isomers is essentially we call the cis-trans isomerism. Okay, so cis is on the same side, and they are next to each other. Okay, the trans is on opposite side. Okay, so I like the trans is an opposite side of the one. And then they give us an example about this case where cis and trans is regarding essentially 2 ligands, okay? And the 2 ligand is possible, and for the case of what they call the square planar. Square planar. Square planar means it's just like this square. And you can think about the metal ion sitting in the center, right? In reality, is actually, if you remember the Chem 1, the Basper theory, this is a one that octahedral in its own nature. It's just we do not show when you have a lone pairs up and down, they just do not show. Okay. And then this square planar, and then when you have, for example, here, I don't know, you guys can see this. This is a platinum, diamine, and chloro. So I will just change this one into, just say this one, change it into platinum. Okay, and having done that, you can put chlorine here. If you choose that, you can choose any corners, but let's just choose this corner. And then if I choose your neighbor, the next to it, and this is a cis. And if you choose an opposite one, this is a trans. Right? So this is when you have this compound with 4 coordinations, such as a platinum, aminino, dichloro compound, and they can have a cis and trans. Yes, they can have both cis and trans when you have a square planar structures. Another example of geometric isomers is one is octahedral. So this is based on the octahedral. Octahedral OH is what we are saying this once again just want to recap. Octa means an 8. Hedral means faces. Right? So you actually, if you draw this plane and the pointing up, you can think about it's like a pyramid with 4 faces. And then if you're going down here, there's another pyramid upside down with 4 faces. That's why it's called the octahedral. It's 8 faces, and it has this kind of very symmetric. And you can think about putting these 2 position and rotating it, and you can say what used to be an axial position now became the plane structures. So and this is a very symmetrical structures called octahedral. Okay, so these are the 2, and then they give you that. What about the case where you have a B2, and then here is a case where the cobalt is sitting in there, and these are the 4 neutral. In the previous problem, it was En2. That's the same thing that you remember the previous problems, right? They are the same one. And then now I am going to put my chlorines. So I can put chlorines here, and I can put chlorines here. Okay, if you want to be consistent with my previous drawing up there. And so okay, so I can, if I put this one here, well, let me try something different. Okay, so if I put here, this is a neighboring. If you look at this is, they are the 90-degree angle for that, right? Whereas this one, if you put chlorine, there's a 1 transposition here. This is, if you put the chlorine, they are the opposite side. So this is a cis, this is a trans. Okay, so this is a cis and this is trans. I think that is the case for these 2. And then this is a little unique for octahedral one, what they call the FAC and MER isomerism. Okay, and this is the one that when I need to go up there, and then FAC and MER isomerism. This is about when you have 3 coordination complexes, and how do they form the complexes each other. So the FER means making a 1 phase, and then MER means is actually coming to a meridian, and which is going through the poles, and then this is what that means. And this is a unique to for those who's having the octahedral with metal, and then there is a 3 compound, and there are 3 compound, and I'm focusing on the one that is 3, that is here. So okay, so if I draw these structures now, same thing. Octahedral means you have plane, and then you have a cobalt sitting in the complexes, because there are, let's say this is a 3+ once more. And then what you can see is, now this one is an example of chlorine, and there are 3 chlorines, and this is an axial, this is an axial, this is going through the other axis. And what you can see that, can you imagine yourself, this is a base plane of pyramid, square plane pyramid with 4 faces showing up, and then I can choose anyone. So let me choose a little different pictures than what this textbook pictures looks like, so that you guys can imagine yourself. I can choose this, and that. How about this? So this one is forming here, forming there, forming this. So this is forming one facet of the chlorine. So this is where I just draw the chlorine. The rest of them is an amine, and that is essentially FAC isomers. Compared to, it's almost like a FAC is on the kind of same side, right? So it is a cousins of cis, right? Quote unquote. Now we don't call it cis because there are 3 has to be there, and they are forming the same side. Whereas if I choose this chlorine here, and chlorine here, and chlorine there. Okay, so instead of choosing this one, if I choose that, and this one is essentially this one forming through the pole and going through inside of this plane, right? And this one, what we call the MER isomers. And this is essentially cousins of quote-unquote trans. Okay, and the MER, if you're looking at the dictionaries, and then this is something called related to the meridian. And if you remember your geographies, is meridian means going through the poles, right? And so that MER coming from that, going through this pole, you are forming this the chlorine complexes. They are making things. And this is a slide that you guys can find out when you have essentially metal with A3B3, because of the three ligands, how they are geometrically put it in when they form these octahedral complexes. They can be on the same side, just like here, or they can go through the pole, and they can form this plane. And that's what we call, this is what we call the FEC. This is what we call MER. I think that I need to stop here, because I think that I'm going to continue to talk about the linkage isomerisms and the orbital energy splitting. This is related to the other problems, but I think that due to the interest of the time, I will stop here, and